In this lesson, students are going to apply dilations and rigid motions to map similar figures one to the other. And we're going to start out just reviewing a little bit the concept of similarities. Two figures are similar if all pairs of corresponding sides are in proportion and the corresponding angles are equal. So we've been using that throughout this unit to set up proportions, to solve for missing sides. And then we know that corresponding angles have to be equal so the similar figures will keep the same shape. So here we have, we're given that triangle ABC is similar to DEF. And what we're going to do is find the missing sides of the triangles here. So this is just a review problem to start off with. I need to find AB, and I need to find FE. So there's X and Y. So all we do is we find the dimensions that correspond to one another. ABC, DEF, so AC and DF would correlate, so the 7 will go with the 14. So I can say 7 over 14 is equal to X over 20. And then you cross multiply, 14X is 140. So X is going to be 10. It looks like the scale factor is 2 to 1, but X is going to be 10. But we'll go through the math over here just to go through it. Okay, so now I need to find Y. Y goes with the 8. Y over 8 is equal to 14 over 7. 7 times Y. That's going to be, what's that going to be? 8 times 4 is 32. Is 112. So it looks like Y is probably going to be 16, I'm going to guess, because that's what it should be. So X is 10 and Y is 16. All right, the other thing we can do, which is that was review. The other thing we can do is actually map AB to DE, or triangle ABC to triangle DEF. And by doing that, what we're typically going to be doing is a combination of dilations and rigid motions. So for example, if I translated triangle ABC using the vector AD, that would put triangle ABC, it would line up, angle A would line up with angle D, but it's still small, right? So there's B prime, here's C prime. So on top of the translation, we need to dilate as well. Now, we can speak in general terms, but remember, for the dilation, for the scale factor, it's always end over beginning. Okay, so it's where you want to be over where you started. So here, the scale factor would be, you could pick any pair of corresponding sides. So if I stick with the 7 and the 14, the scale factor would be 14 over 7, which is 2. So this would be a translation using vector AD, and then a dilation about D with a scale factor of 2. That's how you can map one similar triangle to the other. So that's what we are officially going to be doing. We're going to be doing similarity transformations. So just like we had a rule for congruent figures, you could map them with rigid motions, we have a similar rule for similarity transformations. Two figures are similar if there exists a similarity transformation that will map one figure to the other. So a similarity transformation would be a dilation, and then possibly a combination of rigid motions. It could just be a dilation alone. But it could be a combination of both. So that's what we're going to do. We're going to be mapping and just writing out the similarity transformations to map one similar figure to another. Okay, so in this example, we're given that ABC is similar to DEF. And I want to describe a series of transformations that would map triangle ABC to triangle DEF. So the first thing we want to do, this is like our rigid motions. I want to translate. I usually recommend translating first. So we're going to line up point A with point D. So that would be a translation. So we could do this in symbols or we could do this in words. Translate with the vector A, D. That maps A to D. So if I were to sketch that, now let's see if I can do that. Okay, so that would kind of be B prime, that would be C prime, and that would be A prime there because he's moved. So the next thing I'd want to do is I'd want to rotate. So if I rotate this, I want A prime, B prime to line up with DE. So my second instruction is to rotate about D, mapping A prime, B prime to DE. Okay, so what that would do is rotate it down, and now my triangle kind of looks like this. We're almost there, so let's call this B double prime, C double prime. The last thing we have to do is dilate it, so B prime, C double prime maps to EF, but I can be a little bit more specific because I can use a scale factor. And my scale factor could be DE over AB. Remember, it's always end over beginning. So if we go back here, DEF is where I want to end up. ABC is where I started. So my third instruction would be to dilate from D with the scale factor of DE over AB. Okay, it doesn't matter whether you use the primes, the unprimes, they're the same length. So I just went back to the original. And that's enough to map triangle ABC to DEF. Again, we usually start by translating, and then we rotate, and then reflect if we have to, and then we dilate. Okay, so here's our next example. We're given that BCN lie on a line segment, ACM are also collinear, and the two triangles are similar. So we're going to do this again. We want to map ABC to MNC. So again, this is the end, this is the beginning. So we need to get ABC to MNC. Well, I don't need to translate because they already share a point C. So we're going to relate almost everything from that point. What I can do is rotate. So I'm going to do this one in symbols since I know if that's a straight line, I'm going to rotate about point C 180 degrees. Okay? And that's going to rotate ABC down here, which would look like that. And if I rotated, then this is A prime and this is B prime. After that, all I need to do is dilate. So then I can put then, you're going to dilate from C. My scale factor again is end over beginning. So I could say MN over AB. That's my scale factor. So MN over AB. So that only took two things. It took a rotation and it took a dilation. And remember, it's always end over beginning. So now we have an example where we can use coordinates. The first thing I want to do here, so you're given the two triangles and they're similar. Okay, the first question, what is the scale factor to dilate triangle ABC to match triangle DEF? Well, again, this is the end, this is the beginning, so it's always end over beginning. I can take any pair of corresponding sides. AB is going to correlate to DE, so DE is 1, 2, 3, 4, 5, 6. DE is the end, so it's going to be 6 over 4 reduced down, that's 3 over 2. That's the scale factor to carry AB to DC. Okay, and then we're going to describe a similarity transformation to map ABC to DEF. Okay, we already have our scale factor. So let's see here. There are several correct answers. I'm going to translate using that translation vector CF, and I can write this in symbols. And this is actually 1, 2, 3, 4, 5, 6. You could use CF or you could use 6, 0. I'm applying that to triangle ABC. Okay, so that's going to move my triangle over. So he is now here, if I want to sketch him. Okay, there's A prime, there's B prime. Okay, the next thing I'm going to do is I'm going to reflect over line EF. So I'm going to put then reflect. If I look on the coordinate system, that is the line x equals 3. So I'm going to reflect over the line x is equal to 3. And then, once I do that, so now here's my new triangle. This is A double prime. Now I'm going to dilate. So that's the third thing. I'm going to dilate from point F, and my scale factor is 3/2. And that's enough to map triangle ABC over to triangle DEF. And again, that's only one way. You could have translated A to D and reflected and dilated. You just have to be consistent with your points of dilation. So wherever I translate, that's going to be my center of dilation, and usually my center of rotation too if I have to rotate. Finally, we're given that these 3 points are collinear and ADE is collinear, and these two are parallel. So what we have here are two similar triangles. They share angle A, and since they're parallel, these angles are going to be congruent and these angles are going to be congruent. So they are similar. We want to give a dilation that's going to map triangle ABD to ACE. Okay, and all I need is a dilation because they share point A. And again, ABD is the beginning, ACE is the end. So we're going to dilate from A, and my scale factor could be CE over BD. It could also be AC over AB, any one of those. So if I want to look at different proportions that would work for that, I'm just going to write some proportions down here that are equal, and that'll be kind of where we end today. So correct statements here could be, I could write AC over AB. If I write that, that would be equivalent to the bottom, CE over BD, because that's the entire length here over AB, the entire length here over BD. That would work. You could also represent angles. So the measure of angle A over the measure of angle ABD. So angle A is here, angle ABD is here. Well, that would be equal to the measure of angle A over the measure of angle ACE, because those angles are equal to these angles are equal to each other, and A is always equal to A. So those are some proportions you can write from problems like this, and you'll be given some multiple choice answers where you have to look at the proportions and see if they work or not, so you have to be careful. For example, one that doesn't work, if I write not, AD over AE is not a correct proportion if you say compared to AC over AB. So if we look at that, AD over AE, that's little over big, but this side is big over little, and that's why it doesn't work. So that's a quick introduction to similarity transformations.